Hi, Prof. Our project is a queuing project and we focus on minimizing both the holding inventory and queue time. We are Team 11 and I am Shenke, and my team consists of Ruiying, Yingyu, Qirui, Yufei, and Qingwen. To start off this presentation, I would like to introduce our client to you. Our client is Integrated Decision System Consultancy, IDSC for short. IDSC is a pioneer in ASEAN using operations, research, and management science to solve complex problems. Today, this area of decision technology is better known as advanced analytics, data science, and augmented intelligence. The project we have received from our client has the aim of minimizing holding inventory for some products, each selling at different locations. We are given this sales, inventory level, and reorder quantity for each product for different locations every day. Most of the leftover and unsold items will be returned to the manufacturer at the end of the day. Hence, in order to reduce the return to the manufacturers, we want to minimize both holding inventory and queue time. In this project, we will consider the MMM model to help us to solve the problem. We summarized our whole process into 3 stages. First is to clean the data. After cleaning the data, we will need to analyze this data using statistic knowledge. Lastly, we will apply the queuing data and with our queuing theory from MSO and model the data with FMM model. First, we clean the data we have collected from our client and decided on our variables to be set as number of servers, arrival rate, and service time. We have decided to see the inventory level at the beginning of the day as our server number S, while we see the sales of each day as our customer arrival rate. Lastly, the index for reordering will be our service time. This index is representing whether the store should reorder certain product each day. This derived from the inverse of reorder rate in terms of day per order. We carry out an hypothesis test on whether the sales, which is arrival rate, follow Poisson distribution using the goodness fit test. Subsequently, we conducted a 2-way ANOVA test and found that the mean sales are significantly different across different product and locations. Hence, we need to consider each product at different locations to calculate lambda. And the following are our data. We visualize the sales condition in box plots. Overviewing the sales of each product at different locations, we realize that the sales of different products are quite different. We again did a 2-way ANOVA test to check our point. It shows again that the sales of different products are very different. We then proceed to prove that the sales of all these products follows a Poisson distribution. Before removing outliers, the actual data are quite off from the expected data from a Poisson distribution, with a p-value of 0.008157, which is much smaller than the 0.05, giving us enough confidence to reject our hypothesis. However, we then remove the outliers, giving us a new p-value of 0.084. As this p-value is larger than 0.05, we do not reject our hypothesis of this sale follows a Poisson distribution.
Next, I'm Ruiying, and I'll be carrying on with the next part of our presentation, sharing on how we apply the MSO knowledge and queuing theory on our project. Firstly, let me introduce our queue environment for this project. We first formulate the sales as our arrival rate, lambda, inventory level as our number of servers, and replenishment time as our service time, which is 1/mu. Our project is based on inventory, but is formulated as a queuing project. Why is that so? When our inventory level equals to 1, whereby there is 1 product on sale, if the rate of customer purchasing the product is 1 per day, on average, there is a certain probability that the product will be sold. For any arrival rate at any number of servers, queuing theory can be used to calculate what is the chance of the product being sold. In this case, the service time will be the replenishment time. When the number of inventory increases, that indicates that we have more servers. For example, if the inventory level equals to 10, we regard it as 10 servers. If the sales of the day is fewer than 10, there won't be a queue formed. However, if the sales of the day is larger than 10, a queue will start to form, and the 11th customer can only purchase the product the following day. As the sales for each day is not constant, which has been proven to follow Poisson distribution previously, there will be a probability of all 10 products being sold out and a probability of queue forming. To find this probability, we formulate this project as a queuing model. We first apply the queuing theory. Previously, it has been proven that the average sales follow a Poisson distribution at 5% significance level. To fit in a MMM model, we assume that the reorder rate follows exponential distribution. In order to calculate the minimum number of servers required for stability, we use this formula below. The table then shows the result of the 18 scenarios of different products and locations, with the minimum number of servers required for stability. We then move on to the calculation for the other Q statistics, finding the pi 0, pi I, L, W, LQ, and WQ values respectively according to the following equations. This is the calculated result for product A1 sold in location L1. We started from the minimum number of servers required to ensure stability, which in this case equals to 3. We calculated 5 sets of data for comparison. From the result, as the number of servers increases, the average customer in the queue decreases. The average time spent in the system decreases and the probability of finding no queue increases. Our objective is to minimize both the queue time and the value of holding inventory, which is to make sure every customer is able to buy the product within the day, meanwhile keeping the number of holding inventory low. To ensure every customer is able to buy the product within the day, the average time spent in the system approximates to a value of 1. Thus, we decided to optimize the value by finding the number of servers with W value nearest to 1. For example, for A1L1, we chose 6 as our most optimized number of servers. We then proceed to find the most optimized number of servers for each of the 18 scenarios. From the result, the probability of finding no queue is generally high, which is a good sign. However, there are a few outliers. For example, for B1L3, the probability of finding no queue is only 32%. In this case, we might want to increase the most optimized number of servers despite the fact that the average time spent in the system is low. And with this, I will conclude our project on queuing model. What we have mainly done well for this project. Firstly, we successfully determined the minimum number of servers to be placed in order to ensure queue stability. More importantly, we computed the most optimized inventory level for each of the 18 scenarios by finding the specific inventory level with average time spent in the system nearest to 1. This is to complete our objective of minimizing both holding inventory level and queuing time. However, what we failed to complete is that we were not able to estimate the distribution of service time as an exponential distribution. For this case, we can only estimate and assume the service time in real-life context to an exponential distribution approximately. Moreover, for future plans, we could try out more queuing models such as MGM model or GGM model to compare and determine the model that fits each scenario the best. With more queuing models for comparison, we could achieve a more accurate result for the most optimal inventory level in each scenario in order to minimize both holding inventory level and queuing time. That concludes our presentation. Thank you.